Welcome to The Explainer. Today, we're diving into something absolutely fascinating: how a purely mechanical watch movement achieves extreme durability and precision without a single line of code. I actually like to think of this as the original Internet of Things. Long before we had smart devices strapped to us, we had these incredible mechanical devices that were fully self-contained, self-powered, and literally designed to operate for 50 plus years without ever needing a software update. It's the ultimate antithesis to planned obsolescence. So let's kick things off with the ultimate engineering puzzle. How in the world do you achieve perfect timing while strapped to a chaotic, constantly moving wrist? Think about it. A watch is constantly changing orientation. Because of this, it has to solve the fundamental problem of gravity. The gears and weights inside have to be balanced so perfectly that the pull of the Earth doesn't speed up or slow down the tick as you just go about your normal day. To really unpack how this works, we're going to trace the system through 5 key areas: the defiant mechanical engine itself, how it harvests and stores energy, the famous Swiss lever escapement, the pursuit of isochronism, and finally, how modern materials science is upgrading the standard. Okay, Section 1, the defiant mechanical engine. In a world completely dominated by digital quartz and microprocessors, a purely mechanical watch stands alone. And I really want you to keep this core constraint in mind as we go: zero electronics, no chips, no sensors, absolutely no software. Everything we're about to talk about is hard-coded into the sheer physical geometry of the gears. And since you don't have a computer chip constantly correcting errors in the background, the physical parts have to be machined to incredible tolerances. We're talking just 1 to 2 micrometers. To put that into perspective, a human hair is about 70 micrometers thick. This insane microengineering is exactly why these machines carry such a high price tag. It's not just the raw materials, it's the massive rejection rate during manufacturing if a single gear is off by even a fraction of a hair. So, how does the energy actually flow through this tiny engine? Well, it maps out perfectly. It starts with your physical movement at the perpetual rotor, gets stored in the mainspring, travels down through the gear train, is precisely metered out by the escapement, and finally hits the balance wheel to drive those ticking hands. Moving on to Section 2, harvesting and storing energy. Before a watch can tell you the time, it literally has to feed itself. Invented and patented by Rolex back in 1931, this half-moon oscillating weight is known as the perpetual rotor. It sits in a constant state of unstable equilibrium, totally beholden to Earth's gravity. And it really is a masterclass in weight distribution. If that rotor is too heavy, it's just going to wear down the bearings. But if it's too light, it won't generate enough force to wind the watch at all. It's this beautiful balancing act of mechanical load versus efficiency, harvesting energy from your every gesture. To understand what happens next, we need a quick refresher on a law published by the British physicist Robert Hooke, all the way back in 1676. Hooke's law basically dictates that the extension of an elastic body is proportional to the force applied to it. In simple terms, this law governs exactly how the kinetic energy generated by our rotor can be physically captured and stored. And that brings us to the mainspring. This is a highly engineered coil spring that catches the energy from the rotor. But here's the catch. Because it's a coil spring and not just a simple extension spring, engineers have to safely manage its extreme torque. As it winds tighter and tighter, it holds all the mechanical potential energy needed to drive the entire watch. Now the math here is just wild. 0.033 joules. That is a tiny, practically microscopic fraction of a joule, especially when you compare it to the batteries in our modern smart devices. But because mechanical watchmaking is so hyper-efficient, that tiny little drop of energy is enough to power a well-designed gear train for 40 hours or more. No way, right? But it's true. But wait, what happens if you're really active and you keep winding a spring that's already fully wound? To prevent the mainspring from deforming under all that tension, they built a purely mechanical failsafe called the bridle. It's a pre-tension piece that simply slips against a serrated barrel inside the watch once maximum torque is reached. It perfectly proves that every single action inside this case is a strictly physical reaction. Section 3. The Swiss lever escapement. All right, now we reach the beating heart of the watch, where that stored energy actually gets distributed to measure time. Originally invented by English horologist Thomas Mudge in the mid-18th century, the Swiss lever escapement is arguably the single greatest improvement ever applied to watchmaking. I want you to think of this mechanism as a mechanical dam. It steps in to regulate the massive, rushing river of energy pouring out of the mainspring so it doesn't just release all at once and spin the watch hands totally out of control. Using the power released from that mainspring, the escape wheel moves in tiny, strictly regulated steps. As it moves, the uniquely shaped teeth of the escape wheel push against the pallet fork, literally locking and unlocking the entire gear train as it goes. As the pallet fork shifts back and forth, it hits a balance pin, forcing the balance wheel to swing with it. And that balance wheel is kept in constant oscillating motion by its own tiny little restoring coil known as the hairspring. The amplitude, which is the measure of the rotation angle of this balance wheel, is actually the key indicator of the watch's overall health. This continuous locking and unlocking process, swinging back and forth, is exactly what creates that familiar ticking sound we all know. Through a highly stable frequency curve, this escapement typically creates a beat rate of 28,800 beats per hour, carving up your day into perfectly uniform mechanical slices. Which leads us to Section 4, the pursuit of isochronism. So how does this incredibly delicate system handle the chaos of the outside world? Well, in horology, the ultimate holy grail is isochronism. Achieving true isochronism means the watch maintains a perfectly uniform beat rate as the mainspring unwinds, despite dramatic changes in temperature, despite the dropping torque of the spring itself, and despite passing through everyday magnetic fields. The cause and effect here is absolutely amazing to see. Historically, temperature changes would cause standard steel hairsprings to expand or contract, completely wrecking the watch's accuracy and creating a really messy parabolic curve in the data. But by switching to a special nickel-steel alloy called a linvar, the temperature rate error actually flattens out into a nearly straight line. Plus, this new non-magnetic assembly almost entirely overcomes the effects of magnetism, so your watch won't suddenly go haywire just because you set it down next to your laptop. Finally, Section 5, upgrading the standard. Let's look at how modern material science optimizes this centuries-old physical geometry to push the boundaries even further. Take the transition from the iconic Rolex Calibre 3135 to their updated 3235 movement. When they wanted more performance, they couldn't, just push a software update. Instead, they had to completely redesign the physical physics of the movement, successfully pushing the power reserve up to a massive 70 hours. They achieved this through highly precise mechanical upgrades in what they call the chronoenergy escapement. They literally pierced the escape wheel to make it lighter, which reduces inertia. They made the ruby pallet stones half as thick to reduce physical drag from oil viscosity, and they fabricated parts out of nickel phosphorus to completely dodge magnetic interference. Together, these tiny, microscopic geometric tweaks account for a massive 15% jump in efficiency. By simply offsetting the alignment of the escapement elements, literally just shifting the physical angle of how the parts interact, engineers leveraged pure geometry to squeeze even more performance out of the mechanism. No batteries, no firmware patches, just better physics. It really makes you wonder, doesn't it? In an age where we're basically forced to upgrade our phones and smartwatches every couple of years, is a self-contained, purely physical machine actually the ultimate form of sustainable engineering? Long after our lithium-ion batteries expand and die and our software becomes entirely unsupported, will these defiant mechanical engines just keep quietly ticking on? It's definitely a fascinating thought to leave you with today. Thanks for joining me on this explainer, and hey, keep questioning how the world around you actually works.